So this lesson is about solutions. Much of what you're going to hear should be a review, but there's a few things that are new. So let's start right off the bat with the idea of the definitions of solutions in solute and solvent. A solution is a homogeneous mixture, so it's comprised of more than one pure substance. And it contains typically a solute and a solvent, although there could be multiple solutes. The solute is the substance that gets dissolved, which means it's probably the solid. And then the solvent is typically the liquid. It's what does the dissolving. We work with aqueous solutions, which means that water is typically our solvent. All right, so ionic, why does it do that? Ionic solutions. Not sure why it went through that way, but we'll just go back. Ionic solutions are created when an ionic substance is placed in water and it dissociates. So the word dissociation is what we're going to associate with ionic substances. The ions dissociate, they separate from each other. We learned how to write dissociation equations to show that, and we'll review that in a few slides. So after the ions dissociate, something called solvation occurs. Solvation means that each of the individual ions gets surrounded by water molecules appropriately oriented so that the H's are directed towards the anion, the oxygens are directed towards the cation, and you create an IMFA that's often referred to as an ion dipole because you have an ion being attracted to a polar molecule. So this is an ion dipole, IMFA. We don't really bring it up. It's kind of obvious. We typically just throw them in with dipole usually, but they're really technically called ion dipole. So this is what happens when ionic compounds dissociate. The ions are already there, they just split apart. So that's dissociation. The strength of the solubility is going to be dictated by something that we've become very familiar with, Coulomb's law. I'm not going to spend a whole lot of time going over this. It's very, very much review. Small ions with larger charges are less likely to dissociate than larger ions with smaller charges because of the idea of Coulomb's law. So solubility rules let us predict this kind of thing, which means that if you have something that is soluble, it's going to be easier to pull apart. You can break the lattice energy more easily because probably it either is large ions or small charges. All right, so molecular substances dissolve when you put them in water. The molecules themselves don't break apart. So you put sugar in water and sugar molecules stay as C12H22O11 if we're talking about sucrose. But the individual molecules separate from each other. The carbons, the hydrogens, and the oxygens of a molecule do not break apart. So we're only breaking up IMFAs. We're not separating any covalent bonds. But again, solvation is going to occur. The sugar molecules are going to be surrounded by the water molecules, although this, I guess, is ethanol. So molecular substances dissolve. They don't dissociate. They dissolve. However, there are a few exceptions. There are some molecular substances that when you dissolve them in water, they will form ions. Acids are an example of this. HCl is molecular. The electronegativity differences, there are two nonmetals, the electronegativity difference isn't enough to make it an ionic bond. However, you put HCl in water and you get hydrogen ions and chloride ions. So this process is a third process. So ionic compounds dissociate, molecular compounds dissolve, and on some special occasions, molecular compounds will also ionize. So you get ions forming where there were no ions before. So H and Cl will actually separate into ions even though technically it is a covalent bond that created it in the first place. So this is going to happen with acids. It's also going to happen with organic acids, carboxylic acids, and occasionally alcohols will ionize as well. Not very often, but on occasion you'll get alcohols to some extent ionizing. This means that all of those things form a weakly acidic solution. Excuse me. And that's why sometimes you're going to get conductivity from a molecular substance when you don't expect it, because you have a little bit of ionization going on. So that leads us into the idea of conductivity and electrolytes. So ionic substances dissociate and produce ions in water, and therefore they will conduct electricity. So ionic substances are considered electrolytes because they will conduct water. They will conduct electricity when they're dissolved in water. Molecular substances are typically considered non-electrolytes because they don't conduct electricity. However, those molecular substances which ionize are typically considered weak electrolytes. So molecular substance, you wind up with no ions forming, so the light bulb doesn't go on. You have an ionic substance, you get a whole lot of ions, the light bulb goes on very strongly. However, if you have something like a carboxylic acid where you have a little bit of ionization going on, you get just a very faint glow of the light bulb. So remember that conductivity is the flow of charged particles. And so if you have charged particles that are able to move, you are going to have conduction. If you have no charged particles, or like the ionic substance in solid form, they're not able to move, you're not going to get conductivity. So we can actually use conductivity as a way to kind of predict the ionization of those molecular substances. All right, so focusing on ionic substances, when you put them in water and you start mixing them, you get what we've seen lots of times, double replacement reactions, or what's referred to as precipitation reactions. So if you get an insoluble product forming because of the solubility rules and the fact that you have very strong lattice energy, you get a precipitate. Precipitates by definition are called insoluble products. Now, to show these different precipitation reactions, there are 3 different ways of expressing them. So the typical way is with a molecular equation. So you have the formulas of the ionic compounds. So remember that these are the formula units. They're the lowest whole number ratio of cation to anion. You show the state because the insoluble substance will be a solid. Everything else will dissolve in water, and so you will get dissociation with anything that has is soluble. Then we went on and learned from year 1 that you can write something called a total ionic equation. So in this case, you're going to show all of the substances as the way they naturally occur in solution. So anything that dissociates, anything that's AQ, is going to be separated into ions because they actually are separate in the solution. However, the insoluble product, the precipitate, you're going to keep together as a solid. So here's an example of a total ionic solution. This is kind of a bad example because there's no coefficients here. Please remember that you have to make sure that this equation is balanced, just like the molecular equation was. So you have to have coefficients making sure that all of these ions are going to wind up canceling each other out appropriately. Then you can get into the net ionic equation. And remember that to do that, we're going to take a look at the total ionic and cross out any spectator ions, any of those ions that appear exactly the same on both sides of the equation. And then what you're left with is the net ionic equation. And typically in this case, for a precipitation reaction, the net ionic equation are the 2 ions that come together in order to create the precipitate. So this is showing you the strong lattice energy that gets created when those 2 ions come together. Okay, special note, if you can go directly from the molecular to the net ionic equation, unless you're asked, you don't actually have to write the total ionic equation. So that's kind of nice because the total ionic equation is obviously much longer than the net ionic equation is. All right, so just as a review, remember that the IMFAs that exist, you can have nonpolar attractions, you can have polar attractions, hydrogen bonding, dipole-dipole, dipole-hydrogen, and then this new one that we mentioned, ion dipole, when you have hydration, excuse me, of the cations and the anions in water. Okay, so 3 stages of a solution of a dissolving process, or the process of making a solution. This is going to look a lot like a Born-Haber cycle. So we're not going to spend a whole lot of time with it. You're familiar with Born-Haber cycles. These are much simpler, however. So there are 3 things that have to happen. First off, you have to separate the solute. So that means breaking up the IMFAs. This typically requires energy, so that's an endothermic process. We're going to add energy to it. Second, we also have to separate the solvent molecules from each other. So again, breaking up the hydrogen bonding of water. Again, energy is required, so that's going to be another endothermic process. And then finally, you've got the interaction between the solute and the solvent, and those are attractive forces. So energy is going to be released when the ions or the molecules or whatever undergo hydration or solvation. So then you've got these 3 things going on. We're going to separate the solute, we're going to separate the solvent from each other, and then we're going to combine these guys and form new solute-solvent interactions. So the heat of solution is really equal to the difference between the first 2 versus the third. That's how you figure out your delta H. So you can have an exothermic process or you can have an endothermic process. It really depends how much energy is required for the first 2 and how much energy is released in the third. So again, you can see that this is a very simple version of a Born-Haber cycle. Not nearly as much to have to worry about putting in place. But we still wind up with a heat of reaction as a result. Okay, next up are factors affecting solubility. I think we're going to wait till the next half of the video to do this, so we'll pause here.